During our Zoom lecture, we introduced the definition of what it means for a sequence to be bounded. So we said that means that there has to be this bound M that's positive, such that for all of our values in our sequence, the magnitude of that value, so the absolute value, is less than or equal to capital M. And so if you draw a picture of this, what that means is that if you put a line at y equals negative m and a line at y equals m, the values of your sequence should all fall in that range between those two values. And actually you could have a value of the sequence equal to m because the inequality that we're working with is an inclusive inequality. Remember that when you have absolute values like this, an inequality with absolute values, you can express it as a double-sided inequality. That's saying that the value of a sub n has to sit between negative m and m. And we have a number line representation for drawing a sequence. So I've shown you what it means to be bounded if you're plotting things sort of on an XY graph. This is just saying if I wanted to represent my sequence on a number line, if I look at the closed and bounded interval negative m to m, all of my values in my sequence are going to have to appear somewhere inside this interval. So your entire sequence has to live inside this interval, and there are no values in your sequence that extend past capital M or past negative m. So label that. Entire sequence lives in the interval negative m to m. You're not going to find any values in your sequence that are bigger than capital M. So 2 of the questions we asked in the Zoom activity were, if AN is bounded, does that mean it has to converge? And if AN converges, does that mean it has to be bounded? Now, if the answer to both of these questions were yes, that would say that the expression bounded and the term converge would be equivalent to one another. And that's not something we expect. If we look at this picture that I have drawn on the left-hand side, so I'm looking at this one right here, then notice that we haven't said anything about whether or not we can keep zeroing in our bound, making it smaller and smaller and smaller, and trapping our values in between somewhere. This kind of looks similar to our convergence picture, but the distinction there is that the epsilon band that we're placing around the number a is continually shrinking. So the sequence that I've actually drawn here is just bouncing all around. I have no constraint on whether or not it settles down to a specific number, as long as those numbers that I'm bouncing between all fall between negative m and m. So the answer to this first question is no. An example would be AN equal to the oscillating sequence negative 1 to the n. AN diverges due to oscillation. But AN is bounded by m equals 1, for example. Any term I grab from my sequence, if I put absolute values on it, it's less than or equal to 1. Technically, I could say it's bounded by 500. When you claim that a sequence is bounded, it doesn't mean that you're getting the tightest bound on that sequence. You're just trying to specify a number that's greater than or equal to the magnitude of any number in your sequence. Now, if AN converges, must it be bounded? This is yes, and that's because what ends up happening is the tail of the sequence is what we're worried about when it comes to boundedness. each individual value in your sequence is finite. By definition, it's a real number. So the only way that something could become unbounded is if it trends that way as n goes to infinity. But if you are converging as n goes to infinity, then you know your numbers are all very close to the number a, and there's no way that they're going off to infinity. So the short answer here is yes, but technically this is a theorem, so I'm going to write it down as a theorem and then we're going to prove it. So, theorem. If an converges, then an is bounded. And we're going to use this theorem a lot throughout this course. And it may be helpful to also think of the contrapositive. If an is not bounded, so it's unbounded, then an diverges. So sometimes we might use that fact. So we can use the theorem or the contrapositive of the theorem. So the high level of how this argument is going to go is the first thing we're going to do is we're going to bound the tail of an in an epsilon band around a. Call this bound M1. Now that's only going to bound the tail. That's only going to handle the values where n is greater than or equal to capital N. So then we're going to have to look at bound to the beginning, the points not in the tail. And the way we can do that is there's only finitely many of those numbers, and so you can just use a maximum value when there's a finite list. So we could use M2 to be the max of A1, A2. Just make sure you use magnitudes here because you could have a very large negative number and you need to make sure that negative m is a lower bound for your sequence values. And then once we've done this, we can choose our bound for the whole sequence to be the max of M1 or an M2. So I've drawn a picture here so that I can illustrate what I'm kind of talking about with this high level. Now, we said that what we're going to do is we're going to bound the tail in an epsilon band around A. And something, notice I said here, I said an epsilon band. That implies that I can choose any one that I want. We're not looking for the tightest bound on my sequence, and so it doesn't matter what I choose for my epsilon value. I know that given an epsilon, I can chop my tail. And then once I know where my tail is chopped, then I know what my values are before the tail that get left out, and that's going to be important for my max computation. So let's say I could instead just look at a plus 1 and a minus 1. Here I'm going to choose epsilon. I'm going to essentially choose the tail for epsilon equal to 1. 1 is an arbitrary choice here. It doesn't matter. I could have picked any positive real number. I chose 1 because it's the first nice positive real number. And in doing so, you're going to get the capital N for that tail. So, you know, that N will give me, say, 500. I don't know what the capital N is that puts me in there. It varies as you pick your epsilon. But once I know what that is, if I look inside my band, all of these ANs are trapped in between A plus 1 and A minus 1. Oops, I have those backwards. They're all trapped between the lower bound and the upper limit of my epsilon band for the values in the tail. And this is for all n greater than or equal to capital N. But then I have all these values before my tail that I need to make sure are included in my max computation so that when I pick an actual value for m, like this, when I'm picking my symmetric value, my bound will ultimately include all the values in my sequence. So when I'm looking at the tail, so let's look at the tail. So we said we fixed epsilon to be 1, and we're going to get capital N. We need to show that, like, we need to find our bound, which I referred to up there, find M1, such that AN is less than or equal to M1 for all n greater than or equal to capital N. This is bounding our tail. Now from my picture, the way I've drawn this up here, it appears that M1 would just be little a plus 1. But I encourage you to think about the case where your sequence is converging down here to some negative number. If that's the case, then A minus 1 is going to be the larger magnitude, or the magnitude of A minus 1 is going to be your larger value. So instead, what we're going to do is use an exact argument. Actually, we're going to use the triangle inequality. So I know that we can make the absolute value of AN minus A, we can make that less than 1 for these values in the tail. And I'm trying to say something about A sub n. So I'm starting with A sub n, and I don't see how that's related to A, so I can force that expression to appear in there by subtracting A and adding A. Then I can break this apart using the triangle inequality. And what I get is that that has to be less than 1 plus the absolute value of A. And this number that I found right here is a fixed real number, because A is going to be, I'm going to know what A is. The moment I have my sequence, I know it that it converges, I know what its limit is, A. And so the absolute value of A is a fixed number. It doesn't vary as n changes. Then from there, I just need to figure out what the max value is of the beginning of my sequence. And so this I'm going to use as my M1. And then M2 just amounts from putting all my values in a list. In fact, I can just say M2 is exactly what I've written up here. So I'm ready to write a proof. I'm going to assume that AN converges to A for some A in R. And I'm going to consider epsilon equal to 1. By definition of convergence, there exists a capital N in the natural numbers such that for all n greater than or equal to capital N, the absolute value of AN minus A is less than 1. So, for all n greater than or equal to capital N, if I look at the absolute value of AN and I'm trying to bound it, I can first rewrite that as AN minus A plus A, then I can split it apart using the triangle inequality. So remember where we use that here. This is the triangle inequality. And then I can make my substitution for how I've chosen my tail and the fact that I'm in the epsilon band. Now, I'm not even going to bother defining M1 or M2 in particular. I'm just going to say let M be the max of A1, the magnitude of A1, magnitude of A2, up to the magnitude of A capital N minus 1. This takes care of the bound on the beginning of my sequence. And then I put 1 plus the absolute value of A in there as well. And that takes care of the bound on my tail. Now that we've assigned a value for M, we can just simply note that for all n in the natural numbers, the absolute value of A sub n is less than or equal to M. So A sub n is bounded. Given an arbitrary little n, that little n is either in the tail or its magnitude is accounted for in those beginning magnitudes that we listed for our max. So to point out, this bounds the tail right here. And then this these offer us a bound on the beginning. So together we've accounted for all values in our sequence, and that means that when you converge, you have to also be bounded.